the orientation vector with itself, which is inversely related to the margin. So if you're minimizing that, you're maximizing the margin. So basically all this line is doing is maximizing the margin. But we've got to subject that to constraints. And the constraint is that you have classification accuracy. So you might recognize inside the square bracket, that's the equation of the decision hyperplane. So it's either +1 for the given data, it's either +1 or -1. Multiply that by the actual value of the label, and that gives you a measure of classification accuracy. So basically you're maximizing the margin subject to the constraint that it is that your classifier is accurate, that your classification of all the data is accurate. So straightforward Lagrangian optimization problem. The deltas here are basically slack variables. So they, because if a problem is not linearly separable, you have to allow a little bit of relaxation of this condition that you get all of the classifications right. And the degree of slackness is effectively parameterized by C. So C is a free parameter in a support vector machine, typically, and you either need to cross-validate to set that to a particular value, or you can use something like a radial basis function that guarantees linear separability, in which case you don't need to worry about your deltas at all. So the key thing is when this is dualized, so all Lagrangian optimization problems have a dual form. And when you write it in this dual form, you're basically maximizing this quantity with respect to this constraint. And what we've introduced here are a set of Lagrangian multipliers that are part of the optimization. So the key thing to notice is that what we don't have anymore is the actual decision, the orientation vector for the decision boundary. We only have these sums over kernel quantities with respect to the actual vectors of objects. So that is the optimization problem that we're now solving.
Don't you need to assume that this optimization is convex?
It is always convex.
Why? Because we have okay, I don't know exactly what it is yj something, but so yeah, it is convex. So yeah. Okay.
So it's always convex, but what's most useful from our point of view is that if you solve this, and you can solve this using a whole variety of solvers. Probably the simplest is the ellipse method. But it's not actually the most efficient. But what you always end up with, whichever optimization you use, are a set of non-zero. There are only very, very few non-zero Lagrangian multipliers at the end of the optimization. So very rapidly what you tend to find is that because each of these Lagrangian multipliers is associated with an object, so it's associated with a modality and with an object. And what happens is that all of those, pretty much, will tend towards zero, and the remaining ones are the support objects. So they're the objects that define the hyperplane. So there's this set of objects, we'll call it omega hat, is the set of support objects, and they have associated with non-zero Lagrangian multipliers. And this means that you can actually build, and the end result of this is a recognition rule, so that you're defining your decision. This is your decision rule for at some given input. Your function that defines whether that's +1 or -1, in other words, which side of the decision hyperplane, is basically given by a sum over the support objects. You see, this is now a sum over the set of non-zero objects. So in other words, your decision boundary is a function of the set of support objects. And your offset is similarly derived. So the key point to note at the moment is that there is a set of objects that exists on the continuum between the classes that are neither one thing nor another. It defines a set of objects, and we'll denote those x sub phi for each particular modality. And these later on will be related to the neutral points. So looking now at the kernel fusion problem, that when you combine kernels together, you can combine modalities at the decision level, as we've said. You can forget your problem with missing data and simply solve your problem in each individual domain and then combine your classification output. You could do majority voting, for instance, or you could just add up the sum rule, simply just adds up the output of each individual classifier. So when you've got all of the information, you can straightforwardly construct a kernel in the composite embedding space created by the Cartesian product of the embedding spaces of each individual modality. And that corresponds simply to the sum over kernels. Sum over kernels is also a kernel. And that retains all the properties of any inner products to the Bayes-Mercer conditions. So I've sort of represented this happy situation here. You've got two embedding spaces, x1, x2, that represent the different modalities. There are just four objects here for clarity. You've got kernel similarity measures between each object that help to define the kernel space. I've represented them here as Euclidean distance, just for clarity, because it's related to the inner product. So these correspond to some object in the composite embedding space, the Cartesian product space, and you can see each embedding space as being a sort of down projection from this composite embedding space. And this is straightforward when the objects correlate to each other. So we know what the object correlation is. So any point in the composite embedding space, in the Cartesian product space, equipped with a real number, B, is going to yield a hyperplane decision boundary. So your decision problem in the composite embedding space is essentially your kernel is again built, in terms of the equation for the hyperplane with the bias offset. But now that kernel, as indicated, is the composite kernel, it's the sum. So this means that we can straightforwardly build an SVM training criterion in the composite space, in the Cartesian product space. So here we have, again, the same function that is inversely related to the size of the margin. The only difference being now that it's the sum over kernels. So this is the quantity we're minimizing. We have the slack variables. Again, we have the individual classification decision from here, multiplied by the true label to give us an overall measure of classification performance. So this is the SVM training criterion in the composite space, basically the same as before, but we've got sums over the composite. We've got sums over the component kernels. So we can dualize that. We can represent that in the dual space, and again, the orientation vector, the decision hyperplane, drops out, and we get a problem with Lagrangian multipliers. So again, we're maximizing now this quantity, which has an extra summation term. So this is the same as before, but it has a summation term in here. And when we solve that, you end up with, again, a set of support objects in the composite space, which yields the composite decision rule, which is, again, the sum over the non-zero Lagrangian multipliers. So, in other words, it's defined, the decision hyperplane again is defined by the support objects. but this is the support objects in the composite space. But it's actually the same, it's basically the same as before, but we've got this additional summation, and the same in the bias offset. So that is the case where you have complete correlation information between the different modalities, where every object is represented in each modality. So what happens when we don't have that? Well, let's look at what happens when we have the worst case. This is when the modalities are independently trained. So this is not an untypical situation. If you do multimodal biometrics, and say someone has a proprietary, you have a fingerprint analyzer that comes from a proprietary database, you'll be getting measurements with respect to certain individuals that are unique to that particular modality, and whereas another modality can have another proprietary database of individuals. So it'd be completely non-coincident. So this is not actually atypical. So you can see what happens with the support vector machine optimization when you have this complete lack of coincidence between the objects and the individual modalities. So if you write the kernel fusion training criterion as before, but now what we're doing is splitting up the summation into the kernel specific, into the objects that are specific to that modality, and we have a range of objects that aren't represented in that modality. So this is exactly the same as before, but we've just rearranged the equation just to separate out the inter and intramodal components of it. But the problem is, when our data sets are completely disjoint, essentially this term doesn't exist at all. We've only got that. So that is your problem with kernel fusion with missing data. This is just undefined. So the situation in that completely discontinuous space is something like this. Now you have your embedding space that relates to some set of objects in the composite space, and another embedding space in a different modality relating to some set of objects and also in that composite space, but there's absolutely nothing, there's no information to relate that. So this is completely free-floating with respect to each other. So the neutral point method seeks to address this by finding replacements for the missing sensor values using unbiased neutral points. So the neutral points, remember, are the things that exist in the decision hyperplane of the individual modalities. So they're neither one thing nor another. In other words, they're unbiased with respect to the classification problem. So there are other definitions, obviously, about statistically unbiased, but these are unbiased with respect to the classification problem. So basically, if we take the previous criterion, training criterion, where we separated out the inter and intramodal components, and now we substitute in the missing values, the values that didn't exist before, then we get these terms here. And basically what we find is that if we perform a decomposition of the bias offset in the composite space, that actually this whole set of terms just cancels out. It's not undefined anymore, it's precisely equal to 0. So in other words, in this case, we can simply remove it. And this means that in the worst case scenario, you can actually go ahead and build this composite classifier. So in other words, what you're doing, trying to represent this on the diagram, it's getting a bit busy now. Basically, you have your decision hyperplanes in your individual modalities, defined by the support objects. And these are propagated into your Cartesian product space, in effect. You don't have to select a particular neutral point. It's just enough to say it exists upon this line. And it's projected implicitly into the composite space. And this means that all the things that were previously free floating actually now exist somewhere in this space, which means you can solve the classification problem. So basically what happens when you actually solve the problem, you find that your decision hyperplane becomes linearly separable. So in other words, using neutral point substitution, what you find is you can go through the whole composite optimization problem, and what you end up with is equivalent to decision fusion. In other words, you get the sum of the decisions in the individual domains, which is sort of remarkable, and also very convenient, because this is the asymptotic worst case scenario, and we found that the standard human fallback strategy, which is if we don't have any intramodal information, we'll do decision fusion. This is actually giving you for free decision fusion in this worst case scenario. So this is the asymptotic behavior of the system. And that basically means that classifier fusion is asymptotically equivalent to, that kernel fusion rather, is asymptotically equivalent to classifier fusion under neutral point missing data assumptions. And that's reassuring straight away for this method, because it suggests it's safe, because we know a lot about decision fusion, in particular the sum rule for decision fusion. It's very well behaved because of error decorrelation, so it's very robust to noise. So this means the asymptotic behavior is completely reasonable. So here, we haven't actually computed the individual neutral points themselves. We've just used a mathematical substitute, just to see what would happen in this worst case scenario. But to apply this generally, we do actually have to be a bit more concrete about which neutral point we're going to select. And the simplest choice is basically to choose the neutral point with the minimum norm. In other words, this is the point of intersection between the decision hyperplane's weight vector and the decision hyperplane itself defines a unique neutral point. And that's the minimum norm point on the decision hyperplane. So it's obviously got the same direction vector as the decision hyperplane, and basically you can run this through the calculation to obtain an actual concrete description of this neutral point. So it's actually instantiated this time using essentially the most conservative assumption. So now we can basically substitute that back in to the kernel optimization problem. So wherever we had data that didn't exist in a particular modality, so let's say this object didn't exist in this modality, we can substitute the neutral point in to obtain this modification of the kernel. And that then could be fed directly into the global dual objective function. This is the dualization of the objective function in the composite space. So this means we can now deal with a situation where we've got partially overlapping data sets. So wherever we need to make this substitution, we can go ahead and directly insert it into the optimization problem, and go ahead and solve the support vector machine problem as normal. So basically it's a two-stage process. You have solved the support vector machines in the individual modalities, then that gives you the information to derive the neutral points, which can then be fed into the composite support vector machine optimization problem.
This seems to be something like magic. So basically, just use these neutral points. I mean, there must be some special properties regarding these neutral points. Otherwise, why false? So,
well, this is it. I mean, it's the least biased assumption you can make in the data. So, you've got to do something to. If you want to solve the composite support vector machine problem, you have to make a decision, you have to make some sort of decision on substitution. And this, I would argue, is the least biasing case. And it has lots of very, very nice properties. You're not getting something for free, but what it allows you to do is maximally leverage what data you do have. Because the alternative would be to throw away data where you've only got partial correlation. I'll illustrate that in a point. So this is a concrete application for this method. So basically, multimodal biometrics problem deriving from the biosecure database. So you have a series of modalities. In this case, you have face images, fingerprint scans, and iris scans. So that's 8 data channels in all, 8 images in effect. You've got 3 fingers on each hand for the fingerprints. So it's genuinely a multimodal problem in that there's some correlation between modalities, but it's not complete correlation. For some reason, imposters are more decorrelated than clients. And missing modalities occur for a variety of reasons in this data set. Volunteers don't always complete all the capture sessions. They might turn up for iris scanning but not fingerprint scanning. And that would mean, before, in the old days, you basically have to just throw away that data. You consider that individual wasn't enrolled. So now we're saying that we actually can use this data where people are only partially enrolled. And it can occur for quite unintentional reasons, like on the bottom here you have 4 instances of failure cases of the iris scanner. Well, actually, the leftmost one is actually a good iris scan. But, sometimes people have heavy eyelids or they're blinking at just the moment when the image is captured. And this means that you don't get a good iris scan. If the iris is in the shadow, chances are you're not going to be able to delineate it. If people are wearing contact lenses, it actually works, iris scans work pretty much okay with a well-placed contact lens, but if the contact lens is displaced, then you can't get a good iris scan. Sometimes people just move as the camera is taking its image, in which case obviously you lose the fine detail. So lots of different reasons. So basically there are 333 individuals, and you've got there, those are both clients and imposters. So what you're presented with is lots of pairs of clients and imposters. So you actually get 332,000 pairwise comparisons between individuals. And the key point here is that a quarter of those have missing kernel values. So it's actually quite a large chunk of this data doesn't allow proper pairwise comparison, or at least proper pairwise comparison without using neutral point substitution. So in order to evaluate the neutral point substitution method, we evaluate, and this is carried out by, this particular evaluation is carried out by Norman Poet, sorry. The evaluation is against 5 other alternatives. The first of which is what we call SVM full, so this is just the support vector machine handling only objects that are represented by all the features. So in other words, this means throwing away a quarter of the data set. So this would be what you'd have had to do in the old days, basically. But in this case, or the other alternative is to use decision combination. So SVM sum rule is basically just treating the modalities individually and combining the decision outputs. In this case, because we do have a definite feature space, we can actually compute means. So we can do mean substitution as an alternative to the neutral point method. And we can do that both for the data collectively, but also for the class-specific means. So in other words, you do mean substitution within the particular class. And another alternative substitution method is 5 nearest neighbor substitution. So this is basically where you replace unknown features by the average of the known values of the 5 nearest objects in the feature space, in the composite feature space. So imagine you've kind of got an axis in the feature space because it's undefined, but you can still work out nearest objects to that. So that's one form of substitution. And basically the results look like this. This is the average equal error rate. So that's calculated with respect to an ROC curve. So this is probably the most unbiased form of error measurement. And what you discover is that the error rate is highest for the SVM full. This is where you're using all of your data that has intramodal correlation and throwing away the quarter of the data that doesn't have intramodal information. But that actually loses a good deal of information. Using the sum rule decision scheme, this is where you just work in it, you use all of the data, but you only look at the individual modalities and then combine outputs. That basically gives you a very similar error rate on this data set. Also, the two forms of mean substitution perform quite differently. The class substitution with the overall mean actually performs pretty well. So mean substitution, in this case, when you do actually have a feature space, actually performs pretty well. But for some reason not when you do class-based substitution. That's probably because you're substituting with respect to fewer entities. The 5 nearest neighbour, on the other hand, is substitution method is only marginally better than throwing away the non-correlated information. But best of all is the neutral point method. It's got roughly twice the performance of throwing away the data that isn't correlated, or roughly twice the performance of decision combination where you just combine the decisions in the individual modalities. So that's very encouraging. So basically, just to summarize that, the neutral point substitution method basically now work in any context in which you're combining kernel modalities with missing data. And basically we've shown that it's very well behaved in terms of its asymptotic behavior. Asymptotically it defaults to sum rule decision fusion. And this can be applied in a lot of different areas. So ongoing work at the moment is to apply this basically in different domains, like the medical healthcare analytics, remote sensing. It can be more explicitly incorporated into multi-kernel learning. This is where this is a form of learning that combines kernels but has free weights associated with each kernel. So the sum over any linear combination of kernels is also a kernel, but that gives you potentially another optimization problem in finding the vector of weights. So it can be incorporated in that straightforwardly, which might produce interesting results. And it can also be applied to regression problems. There's no reason why this needs to be just classification. So those are the various references, but probably those are the two main ones in terms of the outline of the theory. There's the first one, identifying the idea, and then this is the details of the biometric experiments. So I think that was I've run a little bit over time. I'll leave it. Thank you very much. Any questions? I think we've lost a compare. So any questions?
Just a curiosity, is there any application also to inconsistent data?
To inconsistent data? Inconsistent in the sense of
generating distinct value, if we take the standard data, most easiest case, Boolean types that are different on different planes, on different modalities. Just wondering.
Yeah, I mean, so I think, I don't think it's, I mean, that would be handled almost as an error in decision fusion. I think, indicated that the neutral point method actually does give you scope for error cancellation. So I guess, outright inconsistency would be handled in that way within it. So I think it would be as well behaved with respect to that as it would be with respect to intermodal error in general. Because if you can actually, the fact that your modalities are not correlated, maybe anti-correlated, can give you some sort of averaging over inconsistency and error. So, it's maybe a talk for another day, but I'm going to work on, how one mitigates error covariance in decision fusion problems. So my inclination would be to say it will behave well. It'd be interesting to try it and not a real problem.
Thanks.
Okay, well, that's it. Well, thank you very much.
Thank you.
Thank you.